Good morning. Let me first introduce myself. My name is Miguel Andrés. I am professor of applied physics at the University of Valencia. And today I will chair this session of OPTOEL 2021. Our invited speaker of today, Miguel Alonso, he is at present professor at the ex-Marseille University, and he is as well the director of the Central Marseille Research. Since an important part of the participants in this OPTOEL are young researchers, I like to say that Miguel Alonso is, in my opinion, a very good example of how a modern, nowadays, a scientific career looks like. Miguel, he is engineer in physics. He got the degree in the Universidad Autónoma Metropolitana of Mexico City. Then he developed his PhD project at the Institute of Optics of Rochester in the United States. After that, he went as a postdoc to Australia for 4 years. He was at the Macquarie University. And then back to Mexico for about 3 years at the Universidad Nacional Autónoma de Mexico. And then again back to the Institute of Optics, where he was assistant professor, associate professor, and finally professor of optics. And it's recently when he has moved to France. I also want to say that in addition to his research activity, I know that Miguel has an important activity in educational events, participating with short courses in international workshops. And in fact, if I am not wrong, it was in one of these workshops where I met him for the first time. Today, Miguel will talk about the POINCARÉ sphere, its generalization, and there are several applications in optics. So, Miguel, please, you can start when you are ready.
Okay. Thank you very much, Miguel, for the kind introduction, and thanks to the organizers for this invitation. It's a pleasure to be there. Muy buenos días a todos. So I'm going to talk about the POINCARÉ sphere, which is a geometric construction that is used mostly for polarization, but that for some reason or another has been following me these last few years is in different areas of research that I work that seem unconnected. This construction comes, or variants of it. So I wanted to discuss it and some generalizations in which I have been working. So let me start by introducing the POINCARÉ sphere for those of you who might not know it or remember it. So suppose that we have a monochromatic beam heading towards us. And then so we know that the electric field is going to trace an ellipse. So we only have x and y components, no z component, because it's is the direction of propagation. And if we don't care about the intensity, which is how big this ellipse is, or the phase, which is where in a specific moment we're on the ellipse, we only care about the shape of this ellipse, then we need 2 parameters to characterize this. And this is what we call polarization. So we have the orientation of the major axis of the ellipse. So for example, it can be horizontal or it can be vertical. So I use this angle phi, and I put phi over 2 so that when I go from horizontal back to horizontal, phi varies by 2 pi. But I also have the ellipticity. And a way to measure it is to box this ellipse into this rectangle and measure this angle here, theta over 2 again. The over 2 is so that when we have circular polarization, theta is pi over 2. When we have linear polarization, theta is 0. And then if we reverse the handedness, theta is minus pi over 2. Now, because these 2 angles look like longitude and latitude as the coordinates of a sphere, then we can represent each one of these ellipses as a point on the sphere where the north pole is right circular polarization, for example. The south pole is left circular, and the equator is all possible orientations of linear polarization. In addition to this, if we add some amount of disorder to the polarization, so the light is not perfectly monochromatic and the path is more complicated, we can do an average that essentially introduces the radial coordinate. Light that is partially polarized can be described by a point inside of the sphere. So this is the classic description of the Poincare sphere. It's a geometric description to represent in an abstract space polarization. I should mention that the Cartesian axes are the Stokes parameters that are things that we can measure in the lab. So the other simple concept that I want to mention is that of geometric phase, which is a phase acquired by a field due to changes in the polarization. So suppose, for example, that we have right-hand circular polarization is incident on a halfway plate. We know that a halfway plate, what it does is takes the polarization and does a rotation around the axis of, let's say, the fast polarization, so this axis, and the retardance is the angle of rotation, so it's halfway plate, so it's a rotation of phi. So this turns right-hand circular light into left-hand circular light. So we're going from here to here. Then I add a second halfway plate that will bring me back up. But if I rotate the second halfway plate with respect to the first, it turns out that we're coming back on a different path on the Poincare sphere. And what that changes, as you can see from the animation here, is the phase of the final beam. So the polarization is going to be the same regardless of this orientation, but the phase is going to change. And this is what we call geometric phase. And in this situation, it happens to be half of the solid angle that we enclose on this path. Turns out that this half solid angle rule, which is what most people always mention when they talk about geometric phase, is valid whenever the paths are geodesics. So, for example, in this paper, that in the interest of time, I'm not going to talk about it much, with Anthony Vela, we look at other geometric interpretations of geometric phases when the paths are not geodesics. Okay, so that was polarization, but people started using the Poincare sphere construction for other aspects of light. And this was initially based on the fact that the Poincare sphere and the Bloch sphere are similar constructions for a subset of this, for a specific description of light. And Miles Paget and Johannes Kortjel proposed studying the structure of simple beams known as Hermite Gaussian and Laguerre Gaussian beams of order 1 in terms of a Poincare sphere. So we know that these simple beams that propagate keeping their shape, for example, the Laguerre Gaussian beam has the shape of a donut. If I look at the face advances in one direction, so it has a vortex. But there's another Laguerre Gaussian beam that looks identical, but the face advances in the opposite sense. On the other hand, there's these Hermite Gaussian beams that have two blobs of light, and they can have different orientations. And it turns out that any of these two can be expressed, any of these Hermite Gaussian beams can be expressed as a linear combination of the two Laguerre Gaussian beams. So we can put them on the Poincare sphere. So the north and south pole are the Laguerre Gaussian beams, the donut beams of different vorticities, and any linear superposition of the two corresponds to a point on the surface of a Poincare sphere that does not talk about polarization, but about the shape of a beam. Now, this is very nice, but it's very limited to this simple type of beam. So much work that follow by other groups aimed at describing the more general type of beam that we see, for example, on a laser cavity, Hermite Gaussian beams of higher orders, Laguerre Gaussian beams of higher orders, these newer Innes-Gauss beams that have an elliptical shape. How can we interpret those beams on something like a Poincare sphere? So the first generalization was to something called the generalized Hermite Laguerre Gaussian beams, which are generalizations of those combinations that I showed you before, but with a higher order. And by higher order, I mean with more oscillations here. So the order of a beam, for example, here is the number of zeros in the x direction plus the zeros in the y direction, or here the number of zeros in the radial direction versus the zeros or phase oscillations on the azimuthal direction. So all these people worked on different generalizations for higher order beams, which this type of beam can be represented again by a point on a Poincare sphere. But what we wanted to do with my postdoc Rodrigo Gutierrez Cuevas and with Mark Dennis is a more general description. And recently we proposed one where any type of this beam, because it has far more degrees of freedom, can be described not by one point, but by many points over a sphere, like the Poincare sphere. And this is based on a construction that Ettore Majorana did for spin systems. So by applying this, we can describe any beam in terms of a collection of points over the sphere. The beams that I described before correspond to the limit where all the points coincide, or are at a point and its antipode. But in general, we have more broad the distribution of the points. So, for example, a specific case that we were looking at is these platonic beams, where the points are distributed on the corners of a platonic solid. And with this, we can have a beam with a given intensity profile with some symmetry. And something else that I should have mentioned is that if we use a system, an optical system with cylindrical lenses, it has the same effect on these beams as birefringence has on polarization. It enacts a rotation of the sphere. So we can, for example, take this beam, rotate it, and rotate it again, and let's say now we put a point on the top, and we transform the beam into a beam that looks very different. It has 12-fold symmetry rather than 8-fold symmetry at the beginning, but it is in a way the same beam because it corresponds to the same collection of points on the sphere. So this representation lets us see some symmetries that are hidden, that are not evident on the profile of the beam, but that are inherent to the space of these type of beams. So that is a wave description, but we were also interested on a ray description. Rays are very intuitive, I find, and they show you, they give you an intuitive idea of where light is going, etc. So with Mark Dennis, we wanted to give a description of how what are the rules behind the shape of a beam that is supported, say, by a laser cavity. And whenever we talk about a beam and we talk about the rays that compose a beam, we need a two-parameter family of rays. We need, for example, for a plane wave, we need all the rays that are perpendicular to the wavefronts. Or for a spherical wave, we need all the rays that are coming from the source. So we need two parameters to specify each ray. But if we break that two-parameter family of rays into one parameter family of rays, we can see that the type of ray families that we use are like this. They're families that, like the beams themselves, have a profile, a transverse profile, that is preserved as the beam propagates in Z, except that it grows a little bit, following in a hyperbolic law. So these families of rays follow the same geometric transformation on propagation as the beams. They keep their shape, but they get slightly bigger. And these families of rays can be more flat, or they can be more round. And they can also go in different orientations. So we can use, again, the Poincare sphere to label this subfamily of rays, because the ellipticity we can encode into the polar angle and the orientation into the azimuthal angle, and this family of rays is then mapped onto a point on a ray Poincare sphere. So if I want to describe a Laguerre Gaussian beam, a beam with rotational symmetry, I need a two-parameter family of rays, so I need to superimpose a family of these subfamilies of rays. So I'm going to use all these that I'm showing different colors. So if I start putting them together, I see that this beam is these rays look like a Gaussian beam. It's a donut. It's an empty circle. We have what we call a caustic, which is a bright region. Is the envelope of the rays, is the inner wall here, and the outer wall as well. So we have two caustics, an outer one and an inner one. And the representation on the Poincare sphere for this beam is then a circle, as shown here. A circle of which is the intersection with a horizontal plane. So it's a horizontal circle. So interestingly, if I now apply the cylindrical lenses that rotate the beam, rotate the Poincare sphere, I'm going to see a change of shape of the beam. And at some point, if I get to a vertical, so I rotated by pi over 2, now I have something that has rectangular symmetry. So this is a Hermite Gaussian beam. So this is a way to see with rays how I can transform a Laguerre Gaussian beam to a Hermite Gaussian beam using a pair of cylindrical lenses. So astigmatism has the effect of rotating the sphere, and it allows us to transform a Laguerre Gaussian into Hermite Gaussian. For the intermediate values of here, for example, the shape of the caustic is not easy to understand. So what I want to convince you for the next few minutes is that this Poincare sphere explains in a very intuitive way the shape of the caustic. So let me come down here, and what this figure here is showing is this black curve, which is the shadow, the projection of this ellipse onto the equatorial plane. So if I go back to the beginning, this was a circle, but as I start rotating the sphere, this turns into an ellipse that goes off-center. Here I show a cross-section of the beam, so I see the caustic here, and I see that the inner caustic acquires this funny shape. Now, to see the connection between this and this, let me introduce another idea here. So suppose that this curve is more general, has this shape here, and I'm gonna look at what happens at this point. I can find a little circle that fits here. It touches this curve and touches the edge of the equator, and it has a center here. There's another circle with the same properties. This bigger circle here is touching the curve right here, and it's touching the edge of the equator here, and its center is here. Now I'm going to move around the curve. If I move around the curve, those two centers of the circles are going to draw curves that ultimately close onto themselves. And now these two curves, which I call the medial axis, happen to have a beautiful property. That is, if I take this circle and I pretend this is the complex plane, this is the real axis, this is the imaginary axis, and then I take the square root and plot the real axis and the imaginary axis of that, I'm doing what we call a conformal mapping. I take this grid and I turn it into this grid. These two curves become the caustics. So this little feature here is this little feature here, but because the square root has a positive and a negative result, I have a copy here. So what we can see is that the caustics of a beam, the outer and inner limits of where the beam is most intense, satisfy a hidden geometrical rule, which is they both map onto curves that are the two medial axes of the shadow of the Poincare sphere. So if I know one caustic, I can map it here. I can find this black curve for which it is the medial axis, and then I can find the other medial axis that then I map here, and I find the second caustic. The two caustics there are intimately interrelated. And this is what we see here. I can, in this case, the two caustics map onto this and this. And no matter what curve we have on the Poincare sphere, we can describe the shape of the beam. So it turns out that this can be used to describe geometric phase in terms of rays or beams. So for example, if I have a Laguerre Gaussian beam and I transform it using cylindrical lenses into a Hermite Gaussian beam, and then I keep going to the Laguerre Gaussian beam of the opposite handedness, and then I bring it back with cylindrical lenses with a different orientation. So I go through a Hermite Gaussian beam in a different orientation and back here. Well, this beam looks pretty much the same as this one, except that if you notice, the colors are not in the same place. That is, the rays form the same global pattern, but they have displaced to a different part of the beam. Each ray is going to be playing on a different part of the beam. I like to think of this as these being dancers in a folk dance group. So they start at some position, then they dance around, and then at the end of their dance, we see the same formation. But if we look at which dancer is where, they have moved. And this happens to explain very nicely the geometric phase of the beam. In this case, the final beam is going to have a different phase, which comes from the fact that rays moved around and they each started with a different phase, so they will end up with a different phase. So this ray description explains very nicely this phenomenon of geometric phase, as well as the phenomenon of the Gouy phase, which perhaps in the interest of time I will skip. If you have questions at the end, I can explain it. Very good. So we've used this experimentally to measure geometric phase and Gouy phase for beams. But let me go back to polarization, because I want to discuss other generalizations of the Poincare sphere. And much of the work that I'm going to discuss is based on an invention by my colleague and friend in Rochester, Tom Brown, which is this glass window is a piece of glass that is subjected to pressure on 3 directions. And that creates birefringence, but it creates a birefringence pattern that is not uniform, but it has a very interesting pattern, which we show here. This is, it shows that the retardance is a linear function of radius, and the orientation of the fast axis, it turns out to go around a uniform angular speed, what we call topological charge -1/2. That is, the rotation of the fast axis goes against the angle that we're going, and twice as fast. We use these windows, for example, to generate different types of beams. So we call something full Poincare beams. These are beams that cover the whole surface of the Poincare sphere in their cross section. So they map the Poincare sphere onto the profile of the beam. Also, we use them to create bottle beams, beams that are very dark at the center, and they become very intense as you move away from the center in the 3 directions. But perhaps the more interesting use of this device is for polarimetry and extensions of polarimetry. So suppose that you have a point source, and that you form an image of that point source. We know that we have the image of a point source is not going to be a point. We have the resolution limit. It's going to be a point spread function. It's going to be a blob of light. However, if you put this stress window in your imaging system on the pupil, and then you filter out, let's say, the right circle of polarization, what you're doing is you're shaping this point spread function in a way that tells you what the polarization is. So for example, if I have a point source that is right circularly polarized, the point spread function is going to be a blob. But if we make it left circular polarized, it's going to be a donut. If it is linearly polarized, it's going to be some croissant shape whose orientation is related to the orientation of the linear polarization. And even if we reduce the degree of polarization, this changes in a different way. So we use this with colleagues here in France to characterize multi-core optical fibers for endoscopic applications. So we have hundreds of independent fiber cores that transmit light, are very, very uncoupled, but we didn't know what happened to the polarization. So what we did is we imaged the light coming out of those cores, and as you can see, each image of a fiber core has a point spread function with a different shape. And from that shape, we can recover the polarization. If we change the input light, the polarization of the input light we're putting into the complete set of cores, we can see how the polarization changes, how each one traces the Poincare sphere, and from here we can obtain the transmission matrix for the fiber core. We can even do this in real time and monitor in real time how the polarization is changing. For example, when you manipulate the fiber. So this stress window lets you measure polarization in a single shot for sparse objects like this. So let me talk about a couple of generalizations of the Poincare sphere for non-paraxial light. So all that I talked about is paraxial, but let me now talk about non-paraxial light, where the Z component is important. Now the Poincare sphere is not enough because we don't have enough degrees of freedom. However, John Hanna in Bristol proposed a representation, it's very nice, using Majorana's construction that I described earlier, and where he proposed describing non-paraxial fully polarized light by 2 points on the sphere. So if the light is not paraxial, and because we can have all three components with different amplitudes and phases, what we have is an ellipse that has an arbitrary orientation in space. So we can describe the orientation and ellipticity of this ellipse with 2 points. And these 2 points happen to have very nice geometric interpretation. They are the 2 points from which, if we look at this ellipse in this direction, in the direction of one of these points, the ellipse looks like a right-handed circle. And same thing for the other point. So these 2 points are unique, and they tell us perfectly the orientation and ellipticity of the ellipse. So if the 2 points are together, we have circular polarization. If they are opposite, we have linear polarization, for example. However, there are 2 slight problems with the representation. The one that I'm going to talk about briefly is it does not have that nice property of geometric phase. So we can generalize the concept of geometric phase, and we would like the area enclosed by these 2 points to equal 1/2 of the geometric phase. So this is something I did with Kostya Plioch and Mark Dennis. And what we did is we wanted to add a bit of Poincare, the properties of the Poincare sphere, to the Majorana sphere. So I represent this by saying, well, this is Mr. Majorana, and I want to make him look a bit more like Poincare. So if I integrate the two, we get something that we call the Poincaré sphere. Later, I realized that a better name would have been to use these 2 syllables instead of these 2 syllables. And we'll have the Macarena sphere. But the paper is published, and we call it the Poincaré sphere. So the Poincaré sphere has a similar interpretation as the Majorana sphere. It has a different, slightly different geometric construction. But the main thing about this sphere is that if we have a continuous transformation of polarization, so we see an evolution of this ellipse, we can calculate, generalizing the 2-dimensional formula, the geometric phase, and this geometric phase happens to correspond to 1/2 of the enclosed solid angles. So this Poincaré sphere takes the nicest aspects of Majorana construction and the Poincaré construction. But this is limited to full polarization. What if we have partial polarization? We have randomness in the field. The field is not fully polarized. Well, it turns out that then we have to describe the polarization with a correlation matrix, and it's a 3x3 correlation matrix. And if we normalize to the intensity, that means that we have 8 independent parameters, and we can use something analogous to the Stokes parameters. There are many conventions for doing this. This is a convention that I proposed in a recent archive posting. It's a tutorial on non-paraxial polarization. So we need 8 parameters to fully characterize non-paraxial partial polarization. So we can construct this vector like the Stokes vector, but this one lives in an 8-dimensional space. And it happens to live inside of a hypersphere, unit hypersphere in 8 dimensions. However, it's very difficult to visualize this. And further, the space in which it lives is not the whole sphere, the whole hypersphere is more restricted. So in that tutorial, I describe by looking at different subspaces, what are the inhabitable regions for the different subspaces in terms of the others. But what I want to focus in the last few minutes is an application of this, which is an application in polarization microscopy, super resolution polarization microscopy. So this resulted from a discussion with my colleague here in France, Sophie Bracelet, who's an expert in fluorescent microscopy, super resolution, especially with polarization, and it ended up with me coming to France essentially to work on this. So imagine that we have a sample with many fluorophores, many molecules that are elongated, and we want to image them with a lot of precision in X and Y, but also in Z, how high or low they are. And also they're elongated, so we want to measure their 3D orientation, so we need 2 angles. And further, they oscillate, they wobble within some solid angle. So we want to measure that solid angle. So we want to measure 6 degrees of freedom here. So what we propose is to use the same or a very similar birefringent element to the stress window, and then separate the image into 2 polarizations and look at the 2 and see if we can recover all these parameters from these 2 images. And it turns out we can, and in an essentially optimal way. So let me show you this in an animation here. If the molecule is not wobbling and is horizontal and is at z equals 0, my 2 images look like the 2 croissants. But if I change the orientation, I change the shape of these 2. If I change the height, I change also the shape of the 2. If I rotate out of a plane, the shapes change, and essentially we can recover all 6 parameters from this. And essentially this is the composition of these shapes into the Stokes parameters. So just to show you results, we implemented this with beads initially. So these are experimental measurements. We simulated the orientation with a polarizer, and we can see how the measurements show the directions of all. Even we change the height, we can recover that. I can show the retrieval. Height is labeled in terms of color. And finally, just to finish, these are measurements with single molecules. So we can measure all these parameters simultaneously in a single shot. And this relies on this description of non-paraxial polarization. So to finish, so the POINCARÉ sphere is a construction that is more than polarization and is more than a block sphere. Its generalization involves higher dimensionality, sometimes can be expressed in terms of a sphere by using several points. So we can either have an 8-dimensional space or a simple sphere but with many points. Ray optical description of beams are passed over the sphere, and many nice geometrical aspects come out of this POINCARÉ sphere description. Birefringent windows allow single shot 2D and 3D, as in this case, polarimetry. I quickly thank my collaborators in the University of Rochester, Fresnel. This is my group, current and past PhD students and postdocs, Hervé Rignon and Sophie Bracelet and their groups in Fresnel, Tom Brown and Nick Bemebekas in Rochester and their groups, and Mark Dennis and Kostya Bier. These are the funding agencies, and I thank you very much for your attention.
Thank you, Miguel, for your presentation. Let me have a look if we have questions in the chat. There is one question from Jose Luis Cruz. He asked, can you foresee applications of this kind of beam manipulation beyond the laboratory demonstrations?
The beams, yes. So these are for the beams that we describe with the sphere. Yes. So Laguerre Gaussian beams, for example, have been used for encoding information in the orbital angular momentum. People have been looking at these Innes-Gauss beams, which are, I didn't get to talk about them much, but this treatment shows you why they're elliptical. They have been used also for encoding information. But in general, yeah, applications like trapping of multiple particles, etc., you can design them to have distributions of maxima that can serve as traps. So this formalism lets you design fields with different geometries.
Let me put you a question myself. I wonder if you have been applying the Poincaré sphere to quantum optics. Do you know any application of this Poincaré sphere for quantum optics?
Yes, absolutely. I did not talk about it. I have not done so much myself, but to quantum mechanics, for sure. So one thing that we submitted recently is this description of particularly of the Innes-Gauss beams in terms of a Poincaré sphere. The regimes that we get, the description that we get, we found this completely analogous mathematically to a quantum model called the Bose-Hubbard-Daimer model, which is something that is used to describe atom gases where you have two species and there's a nonlinear interaction between each species and then some hopping between the two. And that happens to be analogous to the two parameters in the Innes-Gauss beams that come from the cavity that generates them having astigmatism and spherical aberration. And there the quantum aspect is more what for the beams is going from rays to waves, and the quantum analog is going from classical to quantum. But what you're saying is more, if you just stay within light and you have the Poincaré sphere for polarization and you quantize, well, then you have extra restrictions on the Poincaré sphere that are very interesting. But yeah, I would like to look at them.
Okay, let's see. Let me put you another question. You have been talking about geometrical phase in different parts of your presentation.
Yes.
And I understand, well, I don't know too much about geometrical phase, but I would like to ask you whether you can point some practical application of geometrical phase in optics in general.
Yes, absolutely. So one is now there are a lot of phase plates that are based on geometric phase, because when you want to write a wavefront with a complicated phase on a beam, if you use dynamic phase, you have to increase the thickness of the device. But as you start to make more and more phase, that gets complicated, and you're going to have discontinuities if you have vortices, etc. However, if you use geometric phase, you just use birefringence and you change the orientation of the fast axis. There's no limit to how much of a phase ramp you can write on a beam, for example, and you can have vortices by just letting the fast axis of the birefringence go around as you go around the proposed vortex. So many devices for wavefront shaping nowadays use geometric phase. And in a way, the stress window that we're using for microscopy now uses geometric phase. That's something that is, you can think of it that way anyway. It's a way that we use to shape the point spread function to give us the information we need.
Okay, let me have a look if we have more questions in the chat. There is none, so let me just make one more comment or question, I'm not sure. I think that nowadays it's very important to choose the right name for a given property or a given result. And so you are talking about the POINCARÉ, but perhaps Macarena is a better option.
Perhaps Macarena, yeah. I even made this when I give a longer talk. I even make the point, the joke that, well, we have 2 points that describe the evolution. So you can think of, they do this and then they do this and then they do this. Yeah. But one example of that is a paper that I mentioned here, where we called something the full POINCARÉ beams, which are beams that have all the polarization. I think that choice of name made that paper much more cited than other papers that perhaps didn't use the right name. Is unfortunately, there's a bit of marketing when you think of names of new concepts. So yeah, maybe Macarena was better than POINCARÉ.
All right, so I see that there is no further question in the chat. So I think that we can end here your talk, and thank you very much. Thank you very much, Miguel, for this nice talk and for accepting this invitation to participate in OPTOEL meeting.
It's my pleasure, and I wish I were there physically. I hope it will become possible soon.
Well, now that you are in France, it's relatively easier to see you in Spain.
Exactly. Okay, thank you very much.
Bye.